Hello all, welcome to part 8 of the Buffer Overflow Primer video series. Hopefully you enjoyed the last video where we exploited the vulnerable program exploit me by injecting shellcode using HackU. Now there's a small thing which I want to mention before I end the first part of the Buffer Overflow Primer, and that is that if you remember the last example, we basically had to go ahead and point the return address directly to the beginning of our shellcode. Now, and we spent a good amount of time figuring out where this beginning of shellcode actually is on the stack. Now, this problem gets compounded when we do not have the source for the executable, and at the very same time if the executable is compiled without much of debug information. So in order to make things simple, we can actually place our shellcode in a slightly different way. What we can do is, on the buffer, first we can go ahead and create a NOP Sled, which is nothing but NOP instruction filed one after the other. Then we can have our shellcode, and then after that we can have our return address. Now the interesting thing is, because the NOP instruction basically means do nothing, we can go ahead and point our pointer to anywhere within this entire NOP instruction sled. So because of this, regardless of wherever it lands, the EIP lands, the CPU will go ahead and execute the instructions and then finally reach the beginning of the shellcode. And from here on, the shell would be executed. The good thing about this NOP Sled technique is that we do not need to know the exact starting point of where our shellcode is in stack memory. Instead, we can get away by pointing somewhere within the whole NOP buffer, and from there on the CPU will go ahead, execute further, and finally at some time start our shellcode. Well, so that's all for the simple primer on buffer overflow. Sadly, the very simple technique which I just showed does not work in any of the recent Linux systems generally with kernel 2.6 and above. Now let's quickly discuss some of the buffer overflow prevention techniques. The first one, of course, is that the programmer writes secure code with bounds checking in place. Unfortunately, this is generally not possible, and to err is human, and hence programmers will make some mistakes. So what was done is basically to make OS level changes in order to incorporate buffer overflow prevention techniques. The first one is basically NX, or non-executable memory. Now what this is by making the stack, the heap, etc. non-executable memory. Now when the CPU actually finds that EIP is pointing anywhere within this non-executable memory segments, it will go ahead and raise a segmentation fault and not execute the instruction. So by this way, it is not possible to go ahead and store our shellcode onto the stack or the heap. The second technique is ASLR, or address space layout randomization. Now what this does is basically lays out the address space of the program in such a way so that various segments such as the stack, the heap, etc. are in every initiation placed at a random address. Finally, we also have stack smashing protection techniques using stack cookies and canary values. So we will now look at exactly what these prevention techniques are and how it may be possible to still go ahead and exploit the vulnerable program in the presence of these techniques. So let's first look at the NX, or non-executable memory. As a special case, we will look at the non-executable stack case. Now, non-executable stack basically means that even if we go ahead and write the shellcode onto the stack, we cannot point the return address back into the stack. because it is not going to execute and there is going to be a segmentation fault. Now, basically, even though instructions cannot be executed onto the stack itself can still be corrupted. And thus, this does not protect the stack from getting corrupted in any way. So, how can we go ahead and subvert this prevention technique? So we will do this using a technique called return to Libc. Now, what is this? Basically, if we can override the stack, we still control EIP, because that is nothing but the return address stored on the stack. Now, we want to point EIP to something in memory which can help us, let's say, create a shell. Now, why not then go ahead and point EIP into a syscall which is happening inside Libc, right? So we can go ahead, let's say, somehow point it into the system call and to get a shell. And because Libc is mapped into the memory space of most programs, this is going to be a very predictable kind of an exploit. So what's the plan? Basically, we override the stack using the vulnerable buffer. And then we point the return address to the system call within Libc. Now we will look at in the next video how to go about finding the address of the system call in the Libc package in memory. Then we somehow have to set up the argument to system, which if you want a shell would be /bin/bash on the stack. And then finally, when the system call actually returns, we would want to execute the exit call to exit the program gracefully, right? So we'll take the same vulnerable program, exploit me.c, which we have taken in the last video. And let's try and understand a bit deeper as to what is happening. So if you remember, basically we first have a buffer of 80 bytes, then we have the frame pointer, which is 4 bytes, and then we have the return value, which is another 4 bytes, right? So what we shall do in return to Libc is basically, first, we do not really care what is going to be in the first 84 bytes, which is the local variable plus the frame pointer. Then we go ahead and override the return address with basically the address pointing to the system call inside Libc. Now we go ahead and override the next address, which is in higher memory, with a pointer pointing to the exits call inside Libc. Then finally we override the next higher memory address with a pointer pointing to the string /bin/bash, right? So this is how we are going to set up the stack right now. So if you notice, there is no shell code on the stack, simply because with the NX prevention technique in place, we cannot really go ahead and execute any shell code. Instead, what we have done is simply overreturn the return value, point it to the system call, and then go ahead and we have overwritten 8 other bytes with the exit and the pointer to bin/bash. Now, how is this all going to work? Now, pointer 1, if you remember from the previous slide, is nothing but pointing to the address of system, right? And ptr1 is the return address after the main function is going to return. And ptr1, pointer 1, is currently pointing to the system call inside Libc. The next value on the stack, ptr2, is basically assumed to be the return address after the system call returns. Thus, when the system call returns, exit is going to be called. Finally, ptr3 is assumed to be the argument of the system call in Libc, and ptr3 is a pointer to the bin/bash string. Thus, the system call itself is going to invoke a bash shell. Now, let's try and digest the information by looking at the stack once again. So let's trace through the stack. Now, we have overwritten the stack inside the main function in this fashion, right? We have overwritten the buffer variable, we have overwritten the frame pointer EBP, and then we have overwritten the return address, and it currently points to the system call in Libc. Then we have overwritten the next 4 bytes to point to exit system call. And then finally, the third pointer to point to a string /bin/bash. Now, what we actually do is, if you understand, once the main function returns, it is going to pop ptr1 from the stack into EIP, right? Which means now EIP is going to point to the system call inside Libc, and so the system function is going to execute. Now inside system, how would the stack look like? So once main returns, this is what we have currently in the stack, and now we are in the system call within Libc, and this is how the stack looks like just when we enter the system call. So if you think about it, just basically from function basics, whenever we are in a function, what is expected on the stack? The first thing is of course going to be the return address. So when system returns, basically this return address will be popped from the stack, and whatever it points to is going to be executed next. Now this points to the exit system call within Libc, right? Because of which, now once the system call returns, basically the next instruction to be executed is going to be the exit library call within Libc, right? Now once again, within the system function, the second thing expected on the stack is the argument to the system function. And if you remember, the invocation for system, basically the input which it expects is a pointer to the command which needs to be executed. So basically that is what argument 1 is, and somehow we are going to have pointer 3 point to a string in memory which contains /bin/bash. So once again, just to make this clear, we are inside the system call. As soon as the main function returns, we have the return value on the stack, which is ptr2, which is pointing to exit, and argument 1, which is the only argument required for the system function in Libc, is currently pointing to /bin/bash. So basically, once inside system, we are going to go ahead, take argument 1 and invoke the bash shell. Then when system returns, we are going to pop the return value from the stack and execute the exit call, which will exit the program. So basically, now let's move on to a demo of return to Libc, which we will cover in the next video. So hopefully you understood the logic behind the return to Libc exploitation technique in order to subvert the non-executable stack problem. That's all for this video. Would request you to please leave your comments behind and join me in the next video to see a practical exploitation of this technique.